Ma'am, good evening, ma'am.
Good evening.
Good evening, sir.
Yes, Ajay, good evening.
Can start now, sir.
Okay, ma'am. Hello, everybody there?
Yes, sir.
Yes, sir. Good evening, sir.
Yeah, good evening, Dhanlakshmi. Good evening, Varsha.
Good evening,
We were
sir.
talking about few terminologies. Yeah. Few terminologies we were talking about it yesterday in the previous class. We learned about so many concepts yesterday in the last class. Sorry, that is what is an inorganic salt. Inorganic salt is classified into three. There is a simple salt, a double salt, and a coordination compound or a complex compound. And we learned how a coordination compound is prepared. It is prepared by heating or to dryness two simple salts. We gave a lot of examples last class. And we learned some of the terminologies involved. That is the central metal atom. What do you mean by the central metal atom? And what is complex ion? Complex ion is electrically charged. I gave you examples, and we learned the classification of a ligand. Ligand is nothing but a neutral molecule or an ion that donates minimum of one pair of electron to the central metal atom. Those are called as ligands. And we learned the classification of ligands, monodentate ligands, ligands which donates one pair of electrons. And we also learned that anionic ligand, the name has to end with O. Negatively charged ligand, the name has to end with O. We have learned many number of examples, and neutral ligands, we have special names. All right, for carbon monoxide, it's called as carbonyl. For ammonia, it's called as amine, AMMINE, amine. And pH 3 is called as phosphine. Water is called as aqua. NO is called as nitrosyl. And C5H5N, it is called as pyridine, represented by PY. And few of the cationic ligands, positive ligands are called as cationic ligands, and these cationic ligands are few in number, and cationic ligands, the name has to end with IUM. So NO2 plus, the name ends with nitronium. NO plus, the name, and it's called as nitroso ion, and the name of the ion has to end with IUM because it's a positive ion. Therefore, it's called as nitrosonium ion. And this is hydrazinium ion. Hydrazine is NH2. And if this is allowed to react with the H plus ion, a pair of electrons is donated to H plus. So you get NH2 and NH3 plus. So only one donor atom. This ion is called as hydrazinium ion. Hydrazinium ion is a positive monodentate ligand. And polydentate ligand, when we say poly stands for many. When the number of donor atoms are more than one, then it will be called as polydentate ligands. And polydentate ligands are classified as bi, tri, tetra, hexa, goes on like this. Bidentate ligands, ligands which donates two pairs of electrons, is called as bidentate ligand. Here, ethylene diamine. I wrote the structure. I explained the structure, all that in the previous video. Just to have the understanding continuation, I'm trying to talk about the classification of the bidentate, the ligands. So oxalato, it's a negative ligand. This is neutral. Ethylene diamine is neutral. And this is negative ligand and this negative ligand. So this is called as glycinato. Glycinato, N-O it should be called as. Glycinato, G-L-Y-C-I, glycinato. All right, so these all are negatively charged ligands. And we learned tridentate ligand, diethylene triamine, all right, and tetradentate ligand, triethylene tetraamine, so all that. And hexadentate ligand, I clearly wrote the structure and explained that is EDTA 4 minus, ethylene diamine tetraacetate. It is called as ethylene diamine, AMINE, diamine tetra 4 acetate ion. So here you can see 2 nitrogen atoms donating 2 pairs of electron, and 2, 3, 4, 4 oxygen atoms. Totally 6 pairs of electrons are donated. Therefore, it is called as hexadentate. All right, and we learned what is chelating ligands. Ligands which can bind to the central metal atom to form a ring is called as a chelating ligand. And we learned ambidentate ligand which possesses more than one type of donor atom is called as an ambidentate ligand. These all are important questions for 12th. You should be in a position to identify the type of ligand so that you can write the structures, you can name the coordination compounds, all that. So if you fail to identify what type of ligand, then everything goes wrong. See, this is NO2. And this also you can see NO2. Here the donor atom is nitrogen. Here the donor atom is oxygen. So when the donor atom is nitrogen, it's called as nitro. And when the donor atom is oxygen, it's called as nitrito. So ambidentate ligand, when I say a ligand which have more than one type of donor atom will be called as an ambidentate ligand. Here the carbon atom is a donor atom. Here nitrogen, CN and CN. So the molecular formula remains the same here. But here carbon is behaving like a donor atom. Here nitrogen is behaving like a donor atom. And I told you that regarding the pi acid ligand, we will learn in the last part of the topic. And again, I told you, we learned coordination sphere. A complex is represented in the coordination sphere. Ligand with the central metal ion is kept in the square brackets. Now, for an example, if you take Cu, NH3, 4 times and SO4. If you take this is called as a coordination sphere. Whatever is kept in the square bracket is called as coordination sphere. Generally, complex ion is kept in the square bracket. So what do you mean by complex ion? Complex ion will not dissociate to give simple ions. Those are called as complex ions. So coordination compounds is an inorganic salt which maintains its identity in solution state as well as in solid state. That means even when you dissolve it in water, the complex remains intact. This copper and ammonia will not be separated. They will remain as one ion. Now, if you put this copper ammonia in water, copper ammonia sulfate, we will name this later, learning. So this will dissociate to form CuNH3 4 times, 2 plus and plus SO4 2 minus. So this is a complex ion. So it will answer the test for sulfate, but it will not answer the test for ammonia nor copper because these copper ions or the ammonia ions are not free. So copper, any complex ion is electrically charged. It can be positive or negative. Now, for an example, if you take FeCN6 4 minus. So this is a complex ion having negative charge. Here you can see the complex having positive charge. A complex ion can be either positive or what? Negative, which contains the central metal. Here the central metal is copper. Here the central metal is iron, surrounded by definite number of ligands. Here it is surrounded, copper is surrounded by 4 ammonia molecules. Here you can see iron is surrounded by 6 cyanide ions. So ligands in coordination number is defined. Okay, now we talk about coordination sphere. Whatever in the square bracket is called as coordination sphere. Now, what is this coordination number? Number of monodentate ligands attached to the central metal atom or ion is called coordination number. Here, the central metal atom in this complex is copper. Now, to copper, how many ligands are attached? 4. Therefore, the coordination number of copper. Here, what's the coordination number of iron? The coordination number of iron. Iron is a central metal atom. It's surrounded by 6 cyanide ions. Therefore, the coordination number of cyanide is 6. Are you following? What is coordination number? Coordination number is defined as number of monodentate ligands bonded to the central metal atom. Are you following?
Yes, sir.
Yes, sir.
Now, This we were in a little hurry in the last class. We will try to understand this. This is complex. This is complex. And this is the central metal atom or ion. What is the coordination number? We have learned coordination number roughly. In the last part of the class, we discussed about it. So we will try to be a little clear about coordination number. Now, we will take the complex like this, Ag, NH3, 2, and plus. This is the complex, Ag. What is the central metal here? The metal is silver. This metal is surrounded by ammonia is a monodentate ligand. How many ammonia molecules are surrounded by the metal Ag? 2. Therefore, the coordination number of metal Ag is what? 2. If you take a complex like this, CO, NH3, 5 times, Br, and 2 plus. Now, metal is carbon, cobalt here. The metal is cobalt, so the central metal is cobalt. How many ligands we have? NH3, 5 ligands and bromine. Totally 5 plus 1. The coordination number is what? 6. Now, similarly, if I take PT, NH3 twice, and Cl2. Platinum is a central metal. This platinum is surrounded by 2 ammonia molecule and 2 chlorine molecule. Therefore, the coordination number is what? 4. Are you following, students?
Yes, sir.
Yeah. Now, if I take a molecule like this, COEN 3 times 3 plus, what will be this? What does this EN stands for? I told you in the last.
Ethylene diamine.
Ethylene diamine. Ethylene diamine, or what is the proper name for this? This is otherwise called
Ethane 1,2 diamine.
ethane 1,2 diamine. E1,2 amine is what density? What is the denticity of this? It's a monodentate or bidentate ligand?
It's a bidentate.
It is a bidentate ligand. Now, when I say it's a bidentate ligand, we learned the structure also in the last class. NH2, sorry, this is NH2. This nitrogen donates a pair of electron, and this nitrogen donates a pair of electron. It donates 2 pairs of electron. Can I say now ethylene diamine behaves like 2 monodentate ligands? Yes or no?
Yes, sir.
See, it donates 2 pairs of electron. Monodentate ligands will donate 1 pair of electron. A bidentate ligand is donating 2 pairs of electron. Therefore, this ligand will behave like 2 monodentate ligands. When I say ethylene diamine behaves like 2 monodentate ligands, now what will be the coordination number of cobalt here? What's the coordination number of cobalt here?
So 2, sir.
Just look at the structure, what I've written. How many ethylene diamine we have?
So 3, sir. So
And 3. Each behaves like how many monodentate ligand?
2, sir. So change to
So
6,
two.
sir. 6.
6 is the coordination number. 6 is the coordination number. If I take a molecule like this, cobalt, EDTA, all right, 3 plus. Again, the central metal atom here is cobalt. Tell me what will be the coordination number of cobalt here. EDTA is what dentate ligand? I told you today also in the class. What dentate ligand is EDTA? What type of ligand is EDTA?
Sir.
What type of ligand is EDTA?
Sir, 6 denticity, sir. So
It is an
hexadentate.
hexadentate ligand.
Yes, sir.
It donates how many pairs of electron? 6 pairs of electron. Since it's an hexadentate ligand, it behaves like what? 6 monodentate ligand. EDTA will behave like what? 6 monodentate ligand. When EDTA behaves like 6 monodentate ligand, the coordination number of cobalt becomes what? 6. Are you following?
Yes, sir.
Did you understand, everybody?
Yes.
Followed? Yeah. Now, the last terminology, what you remember, is called as ionization sphere. This ionization sphere is also called as counter ion. So, the ion which is present outside the square bracket is called as ionization sphere. It is ionizable. So, what is counter ion? Counter ion, now for an example, if I take a molecule like this Cu, NH3, 4 times SO4. This is called as coordination sphere. It's in the bracket. It's a complex ion. So outside the square bracket, whatever ion is present, that's called as counter ion. Counter ion. Sometimes it's called as ionization sphere also. It's called as ionization sphere. Actually, this is wrong. So coordination sphere and ionization sphere means the same. Whatever is in the square bracket. The outside, whatever the ion is present, is called as counter ion. Here in one of the material, they have written ionization sphere as the ion which is outside the square bracket. So I have taken this for our understanding. All right. So coordination number is clear.
Yes, sir.
Is coordination number clear?
Yes, sir.
Today we are going to learn few questions on the basics of coordination compounds, and we're going to learn the naming part of the coordination compound, possibly the naming IUPAC nomenclature. We'll be learning. I hope that we'll be learning that. All right, let's see. Now, one of the question, what's there on the screen is the ligand NCH2 CH2 NH2 thrice is. NCH2 CH2 NH2 thrice is. What is that? Now, totally we have how many pairs of electron donors? See, nitrogen will have a lone pair of electron. Here also we have a nitrogen. How many nitrogen is here? The brackets. So I can write like this.
Three
NH2
nitrogen.
CH2 CH2 NH2. I can write like this CH2 CH2 and NH2. I can write here CH2 CH2 and what? NH2. So how many donor electrons we have? All nitrogen will have a lone pair of electron. So it's 1, 2, 3, and 4 donor. When a ligand can donate 4 pairs of electron,
Tetradentate.
it will be called as a tetradentate ligand. It will be C. It will be called as tetradentate ligand. Which of the following, the next question, which of the following is a tridentate ligand? EDTA is an hexadentate ligand. Hexa. Here this is oxalato ion. It is a bidentate ligand. Nitrito is a monodentate ligand. Monodentate ligand. Mono. And diene. What do you mean by diene? Diene. Diethylene. Diethylene. So the structure of this is 2-ethylene molecule. We have write 2-ethylene molecule like this. When these ethylene molecules are allowed to react with ammonia, excess of ammonia, the pi bonds break. The pi bonds break. The pi bonds break here. Now the pi bonds break, and what happens? NH2 gets bonded to this carbon, and NH2 gets bonded to this carbon. All bonding takes place to balance what? Their valency. Nitrogen and H gets bonded to these 2 carbon atoms. So we have 3 pairs of electron donors. So this is called as diethylene triamine. Diethylene triamine. This diethylene triamine is abbreviated as DIEN. So the name of the answer for this question is option C. Diethylene triamine. Are you able to follow the structures on the board? Yes. Which of the following ligands form a chelate? What is a chelate ligand? Chelate means a polydentate ligand. Polydentate ligand. Polydentate ligand means ligands other than monodentate is called as polydentate ligand. Ligands which can donate more than 1 pair of electrons is called as a polydentate ligand. Chelate means, or a polydentate ligand, all right, we can define like this: a polydentate ligand which can form a ring with the central metal. So ligands which can form a ring with the central metal atom or ion is called as a chelating ligand. Now, acetate is a monodentate ligand. Acetato, CH3COO minus, is a monodentate ligand. Cyanide ion is a monodentate ligand because it can donate only 1 pair of electron. Ammonia is a monodentate ligand. It can donate only 1 pair of electron. But oxalato, all right, negative ions has to end with what? O. Cyanido, all right, acetato. Now, oxalato, it is COO minus, COO minus. It can donate two pairs of electrons. Now, if this oxalate is allowed to react with metal, now these electrons are donated to metal to form a bond. Now you can see a ring is formed. A closed structure is formed. Closed structure. All right. These kind of ligands are called as chelates. So the answer for this question is option B. Ligands which can form a ring with a central metal atom or ion is called as a chelating ligands. Okay. So it is bidentate or any polydentate ligand can behave like a chelating ligands. Which of the following is not a neutral ligand? Water is a neutral ligand, ammonia is a neutral ligand, carbon monoxide is a neutral ligand. ONO, it's nitrito. Nitrito. The name is O. It means it is ONO minus, NO2 minus. This is called as nitro. And this is called as nitrito, ONO minus. So ambidentate ligand. Here nitrogen is a donor atom. Here oxygen is a donor atom. So it's an example for ambidentate ligand. And this is not a neutral ligand. It is an anionic ligand. It's a negatively charged ligand. The name has to end with O. The next question. Ammonia acts as a very good ligand. Ammonia acts as a very good ligand. But ammonium ion does not form a complex. Ammonia acts as a very good ligand, but ammonia do not form a complex because ammonia is a gas while ammonium ion is in liquid form. Ammonia undergoes sp3 hybridization while NH4 plus undergoes sp3 dehybridization. Ammonium ion does not have any lone pair of electrons. Ammonium ion has one lone pair of electron while ammonia has two lone pair of electrons. Now, in ammonia, the nitrogen atom, atomic number of nitrogen is 7. The electronic configuration is 1s2, 2s2, and 2p3. It has 5 electrons in the outermost orbit. Now, this 5 electrons, we represent it like this by means of dot. The number of outermost electrons we represent by means of a dot. This is called as Lewis dot structure. And each hydrogen atom has 1 electron. We represent 1 electron of each hydrogen. 2 electrons are shared to form a bond. So I can simply tell in ammonia, we have a lone pair of electron. Since ammonia has a lone pair of electron, this ammonia can donate a pair of electron to the metal to form a coordinate bond. Ammonia forms a coordinate bond, no doubt about it. But if I'm talking about ammonium ion, how ammonium ion is formed when this ammonia is reacting with an acid? So acid is represented as H+. This ammonia donates a pair of electron to H+, and you get NH4 plus ion. So in NH4 plus ion, no lone pair of electrons. Since it has no lone pair of electrons, this ammonium ion will not donate electron to the metal. Therefore, coordinate bond is not formed, or complexes is not formed. All right. So ammonia can behave like a ligand, but ammonium ion cannot behave like a ligand because it does not contain of electrons. Hence, the answer for this question is ammonium ion does not have any lone pair of electrons. Therefore, it does not form a ligand, or does not behave like a ligand. It does not form a coordination compound, or it does not form a complex. So answer is option C. Followed, students?
Yes, sir.
Yeah, good. The next one, among the following, which are ambidentate? Among the following, which are ambidentate? SCN minus, NO3 minus, NO2 minus, and C2 minus. Oxalato is not a bidentate. It's not an ambidentate because only oxygen is a donor atom. Here, NO3 minus, only nitrogen is a donor atom. Therefore, this is also not an ambidentate. But when we take SCN minus, a sulfur can donate electron, or you can have NCS minus, nitrogen can donate a pair of electron. Therefore, cyanato, thiocyanato. So these two will be behaving like an ambidentate ligand. Likewise, NO2 minus. Nitrogen can behave like a donor, or oxygen can donate a pair of electrons. So both of these are ambidentate ligand. What do you mean by ambidentate ligand? Ligands which have more than one type of donor atom, or ligands which can get bonded to the central metal atom in more than one way, is called as an ambidentate ligand. Here it can get bonded through sulfur. Here it can get, metal can get bonded through nitrogen. Here metal can get bonded through nitrogen, or here the metal can get bonded through oxygen. But you can see the molecular formula for both these are same. Therefore, this is called as, these two are called as ambidentate ligands. Hence, the answer for this question is option A, 1 and 3. This and this are ambidentate ligands. Followed?
Yes, sir.
Yes,
The
sir.
third question, the next question. Which of the following will not show chelation? Which of the following will not show chelation? Which of the following will not show ring formation? Chelation means ring formation. Chelating ligands will form rings. So which of the following ligands will not show chelation? This EDTA is an hexadentate ligand. DMG, dimethyl glyoximate, this is a bidentate ligand. Bidentate ligand. Ethylene diamine, this is a bidentate ligand. And thiocyanato is a monodentate ligand. So which will not form a chelate? Which is not a chelating ligand here?
So the option D.
Option D is yes. Option D is a
So option D, sir.
monodentate ligand. Yes, it is not a chelating ligand. So this is a monodentate ligand, thiocyanato. It will not form a ring. Therefore, it is not a chelating ligand. The next question, the charge X and Y on the following ions are. The charge X and Y on the following ions are. The oxidation state of cobalt is +3, oxidation of iron is +2 in their respective complexes. Now I'll work one of the complex. The second complex, let's see anybody can help me. This is the complex they have given. The charge on this complex, they have marked it as X. All right, now I told you in the beginning of the class, you should be in a position to identify the type of ligands in order to work problems and other concepts in this chapter. Chlorine is what type of ligand? Chlorine is what type of ligand? Is it a monodentate ligand, bidentate,
The
tridentate?
monodentate, sir.
Okay, monodentate. It's positive, negative, neutral.
It's a negative.
Negative. How many negative charge? 1,
So
2.
four. Yes, sir. 4.
1, sir.
1. Cl minus. Minus means what? Cl minus 1.
Four
So
and
1 in minus 1 into 4 is how much?
-4, sir.
Ammonia is what type of ligand? Ammonia is a
So-
neutral
It's a
ligand.
neutral, sir.
Neutral ligand. 0 into 2 is what? 0. Cobalt, they've given oxidation state to be what? +3. +3. Cobalt, they've given oxidation state to be +3. So what will be X now? X will be 4 minus 3. It will be +1. The oxidation state X is +1. So what will be Y in case of this complex? FeCN6 and Y. Tell me, the charge on this ion, they've given it as Y. Cyanide is what type of ligand? Cyanide is what type of ligand?
Sir, it's a monodentate. sir.
Monodentate. Whether it's negative, positive, and neutral.
Negative, sir.
How many negative charge cyanide has?
So 1. -1.
One. -1 into 6 is how much? 6
So
cyanide
minus-
ions here, -6. Iron, I don't know. I take it as what? I don't know. They've given here the charge of
+2, sir.
+2. +2. So what will be Y? Y will be 6 minus 2. It will be what? +4. +4. What's the answer for this? So the answer for this will be,
So
this will be what?
So Y will be
-1? No, here it should be what? Oh, is there a mistake I made?
Said Y
yes,
is
sir. It's
-4,
-1,
sir.
sir.
Y.
Why is?
-4, sir.
Why it is -4?
So because minus x plus 2.
Oh, minus 6 plus 4. See, I made a mistake. This is minus 4. That's fine.
So y
But
is
what
minus
about
4 and
this?
x is also minus
This is
1.
minus
sir.
1. Oh,
Yes,
I
sir.
made a mistake. This x is equal to minus 1.
Minus 1. sir.
Minus 4 and 3 is minus 1. Yeah. So the answer for this question is option C. Thank you. Thank you. Right. All right. So these are the few questions what we've learned with the introduction of the coordination chemistry. Again, I'm telling you, kindly go through the types of ligands. When you go through the types of ligand, when you understand types of ligand, maybe some of the topics what we're going to learn later becomes easier. Anyways, the next is complexes of two types. Homoleptic complex, homo stands for same. Leptic stands for ligands, complexes. Complexes in which the metal ion or atom is linked to only one kind of donor atom, or simply we can say only one type of ligands are called as homoleptic complexes. You can see here, cobalt is the central metal atom. All the 6 ligands are what? Ammonia. Since all the 6 ligands are ammonia, we can say this complex is an example for homoleptic complex. It's a 2-mark question for your PU 12th standard. All right. So what is homoleptic complex? Homoleptic complexes are complexes which contains only one type of ligand. Those are called as homoleptic complex. Followed?
Yes, sir.
The next is heteroleptic complex. What do you mean by hetero? Hetero means what? Different. Complexes having different ligands will be called as heteroleptic complexes. Now look at this complex here. CO, NH3, 4 and Cl2. CO is a metal. Ammonia is a ligand and chlorine is also a ligand. So this metal is bonded with 2 different ligands. When the metal is bonded with 2 different ligands, they are called as heteroleptic ligands. Complexes in which the metal atoms or ion is linked to more than one type of donor atom or one type of ligand is called as heteroleptic complexes. So what do you mean by heteroleptic complexes? Complexes in which the metal atom or ion is bonded to or linked to more than one type of ligand is called as heteroleptic complex. Followed, students, these two. See, whenever they ask you the question, I am finding nowadays, whenever they ask you a question, students are writing only the reactions, right? So you should write the statements also. Now, for this question, what do you mean by homoleptic complex? It means you have to give a statement, define it, or explain what's the term, and then you have to give 1 or 2 examples, minimum 1 example. All right. So examples are important so that you will not lose marks in your exams. You have learned IUPAC nomenclature for organic compounds in your 11th standard.
Yes, sir.
IUPAC stands for International Union for Pure and Applied Chemistry. So likewise, coordination. See, organic molecules are millions and millions. Number of organic compounds are more. Therefore, we have to follow a set of rules in order to name the organic compounds. Likewise, these coordination compounds are also many in number. So you cannot give specific names for those because it also in millions, numbers, more number. Therefore, we need to follow a set of rules to name them. Those set of rules are given by IUPAC, International Union for Pure and Applied Chemistry. International Union for Pure and Applied Chemistry. All right.
Yes, sir.
I have a problem with this. Yeah, okay. This board mine is not working. Suddenly something is happening. All right. So the rules we will try to understand. Now, if you take an example of a complex like this, K4FeCN6, we will take this complex like this. Now, I will be rush through and finish off with the naming rules, and then we'll try to name many number of molecules possible. Now, this will dissociate in water. Now, tell me, K4FeCN6 will dissociate in water to form how many ions? How many ions? How many ions it's formed? How many ions it is formed? I've written it on the board.
4, sir.
So
4 ions, huh? 4 or 5?
5.
4 K plus and
Sir,
1
yes, sir.
efficiency
4 plus
spoon.
1, 5, sir.
Totally 5 ions. Likewise, if you take this example, CuNH3 4 times and SO4, this will dissociate in water to form CuNH3 4 times 2 plus and SO4 2 minus. How many ions this is formed?
2 ions.
2 ions. That's good. That's good. Now, in the first example, I can say potassium is the cation. Positive ion is called as cation. And FeCN6 is what ion? Anion.
Anode.
An ion, not anode. An ion. All right. Negative ions are called as anions. Positive ions are called as cations. Now, in the second example, you can see this complex ion is the cation. And the sulfate ion is the anion. Are you in a position to identify this? What is cation and anion? Simple.
Yes, sir.
In a
Yes, sir.
complex, you should see what is that outside the brackets, outside the square brackets. If outside the brackets we have any metals, it will be positive. If we have outside the square brackets any non-metals, it will be negative. If the counter ion is negative, the complex will be positive. If the counter ion is positive, the complex will be negative. That's how you understand whether it's a cationic complex or anionic complex. So in the first example, this is an anionic complex. And here this is a cationic complex. Now, why I'm telling you all this is the first rule in IUPAC to name a coordination compound is the positive part, the cation is named first. The cation of the coordination compound is named first, and it is followed by the negative part. That means the anion has to be named after naming what? The cation. So in the first example, what you will name first? Potassium, followed by the complex. In the second example, what you will name first? The complex, and the counter ion you will name second. Did you understand this? Did you understand this point, what I'm telling? So when you name the IUPAC, what's the coordination compound, first the cation has to be named, and then the anion has to be named. No problem with this?
Yes,
The
sir.
first rule.
Yes, sir.
Yeah. The second point is, if the ligands are, see, the ligands are named first if the complex ion, whether it is an anionic complex or a cationic complex, when you're naming the complex, you have to name the ligands first. When I say name the ligand first, followed by the central metal. Ligands has to be named first, followed by the central metal. The prefixes di, tri, tetra, etc. are given to indicate each kind of ligand present. Each kind of ligand present. The ligands are named first, followed by the central metal. Now, in case of the first example we will take, right? The cation is potassium. See, for the counter ion, I am not giving tetrapotassium. I am not giving you the prefix. Because the counter ion, the charge is balanced later. I will tell you how it is balanced later. Now, for counter ion, no prefixes. So even though I have 4 potassium ion, I just write it as potassium. Once I have named the potassium, I have to go for the complex. Once I've named the cation, now I have to go for the anion. The anion is a complex here. When the anion is a complex, you have to name the ligand first. What's the ligand here in this complex? What is the ligand here in this complex?
Cyanide, sir.
Cyanide.
Cyanide.
How many we have?
6, sir.
So
6.
Minus.
Therefore, it is called as hexa. Cyanide is a negative ligand. Therefore, the name has to end with what?
So
O.
cyanide.
Cyanido. Potassium hexacyanido. This hexa is given as a prefix here. Hexa is given as a prefix here. I have not completed the naming. We will complete the naming part a little later. I have not named the metal here. All right. Now, if you take this as a complex, CuNH3 4 times, it's a cation here. So this will be named like tetra amine, AMMINE. See, tetra and no space between the prefix and the ligands. Tetra amine. Copper is a metal. I'm not naming the metal now. I'm not named this full. I've just named the ligand. Prefix I'm talking about, so I named. Yes or no? Yes or no?
Yes, sir.
Now, if I take ethane 1,2 diamine. See, this is a ligand. Ethane 1,2 diamine is a ligand. In the ligand itself, I have a prefix. In the ligand itself, we have what? A prefix. Di is a prefix. Can you identify that? Children, are you following? In the ligand itself, we have a prefix. When in the ligand we have prefixes, we have to give special type of prefixes. What are that special type of prefixes? For 2, you give it as bis. For 3, you give it as tris. For 4, you give it as tetrakis. And for 5, you give it as pentakis, and it goes on like this, KIS, right? It goes on like this. So this is called a special type of prefixes. Now, I'll give you an example. If you take CO, En thrice 2 plus, 3 plus, En thrice 3 plus. Now, En is what? Ethylene diamine or ethane 1,2 diamine. So how will you name this? I name this as what? Tris.
Tris.
I-
Ethane 1,2
Ethane, yeah, 1,2
diamine.
close the brackets. And we'll write later. We'll learn the naming of the metal later. You understood the difference between the di, tri, tetra, and bis, tris, and tetrakis, and pentakis going on like that. So when ligand itself contains a prefix, then we give special type of prefix. That's given as bis, tris, tetrakis, pentakis. Followed. So did you understand?
Yes, sir.
Yeah. The third point here is polynuclear complexes. In polynuclear complexes, bridging group is indicated. In a polynuclear complexes, the bridging group is indicated in the formula of the complex by separating it from rest of the complex by hyphen. In polynuclear complex, a complex with 2 or more metal atoms, bridging ligand, which links 2 metals is denoted by a prefix mu. See, bridging ligand. Now, this is metal 1 and this is metal 2. A different metal or the same metal it can be. If there is a ligand like this, OH, and if there's a ligand like this, NH2, see, there is a bridge formed between these 2 metals. When I have a bridge formed between these 2 metals, these ligands has to be given a special prefix called as mu. And this is hydroxo. So mu, hydroxo. All right. So if we have a bridging ligands, so bridging ligands will be between the metals. We can have more than 2 metals, 2 or more metals. In the previous examples, what we spoke about, these all are not bridging ligands. These are not, but only 1 metal atoms we have in the complex. Since we have only 1 metal in the complex, these cannot be called as a bridging ligand. These cannot be called as what? The bridging ligand. Followed what does bridging ligand means? You followed metals. Now I can take cobalt and OH and cobalt, like this cobalt metal. So this will be called as a bridging ligand. So bridging ligands will be bonded to 2 or more metal atoms. Or when a ligand is bonded to 2 or more metal atoms, then they are called as a bridging ligands. Now the fourth point is naming the ligand. The different types of ligands, neutral, negative, or positive, are named differently in the complex compound. So naming the ligands, different types of ligands are named differently. The complex species having negative charge, the name of the ligand ends with, name of the metal ends with what, AT? This is wrong. It is naming the metal. It's not ligand. Naming the metal. See, when the complex species has negative charge, the name of the metal ends with ATE. The name of the metal ends with AT. Now just observe this. Just observe this. Here, K4FeCN6, FeCN6 is a negative ligand. When we have FeCN6 as a negative ligand, the name of the metal has to end with what? AT. Name of the metal has to end with what? AT. So I don't write it as iron. It is called as ferrate. Just iron is also called as ferrum in other language. So you can see it is named as what? Ferrate, ATE. But it's a cationic complex. Metal is positive here. Complex is positive. When the complex is positive, the name of the metal will be retained as copper itself. Copper itself. Did you understand? If the metal is present in the negatively charged complex, then the name has to end with what? ATE. For iron, metal in negative complex. Metal in negative complex. Now, for an example, it's here. It's here. No point writing again. See, iron is named as ferrate. Silver is named as argentate. Tin is named as tannate. Copper is named as plate. Gold is named as orate. Lead is named as plumbate. All the name has to end with what? ATE. All right. When the complex ion is negative, then the name of the metal has to end with AT. For some elements, the ion name is based on the Latin name of the metal. For example, argentate for silver. Some such Latin names used with the suffix ATE. So all these are Latin names: cuprate, ferrate, argentate, all these are plumbate, all these are. Now, I clearly told you, if the metal is in a cation, metal in cationic complex, metal in cationic complex, the metal will have the regular name. If it is iron, we name it as iron. If it is copper, we name it as copper. If it is silver, we name it as silver. Only in the anion you can see it is named as what? AT. In a positive cation, the name of the metal will be retained. All right. Points
Yes,
of
sir.
attachment in the case of unidentate ligands with more than one coordinating atoms. So you know what is ambidentate ligand? Ligands which can get bonded to the central metal atom in more than one way is called as ambidentate ligand. The point of attachment in case of unidentate ligands with more than one coordinate atom is either indicated by using different names for the ligand, example thiocyanato, isothiocyanato, or by placing single donor atom attached, the name of the ligand separated by hyphen. Look at the example here. All right. Look at the example. Now here you can see that we don't worry about the name of the complex now completely. We have not learned the procedure rules correctly. Here chromium is the metal and sulfur is the donor atom. Since sulfur is donor atom, we write it as what? S. Here NCS, here SCN and NCS. Here nitrogen is a donor atom. Therefore, we represent it as what? Nitrogen. Are you following? So when we have an ambidentate ligand, you should indicate the donor atom. Now tell me what will be the donor atom here and what will be the donor atom here. What will be that donor atom here? I'll write it as what? What will be the donor atom here?
So, N, sir.
Nitrogen.
Nitrogen.
Here, what will be the donor atom?
So, oxygen.
So you should represent like this, N and O. We'll learn the complete exam, the procedure, the rules, and then we will see. The fifth point, the name of bridging group, name of the bridging group. If a complex contains two or more central metal atoms or ions, it is termed as polynuclear. If a complex contains more than one or more central atoms, they are called as polynuclear. In certain polynuclear complexes, ligands may link two metal atoms or ions. Such ligands which link two metal atoms or ions in polynuclear complex is termed as bridging ligands. We learned what is bridging ligands and we give a prefix mu. I just observe here. This is a metal and this is also a metal. You can see NH2 is a bridging ligand. NH2 is linked to both the metals. So if NH2 is a bridging ligand, it is named as amide and I write it as mu. Why do we write it as mu? because this mu clearly indicates it is a bridging ligand. All right. Now you can see here, OH, hydroxo is a bridging ligand. So I represent it as mu, hydroxo. And we will learn why it is this, all the naming part completely, we will do it later. Now, the next, did you understand what is bridging ligand? Students, did you follow what is
Yes,
bridging ligand?
Yes, sir.
Others?
Yes, sir.
Yeah, good. Right. Now, if any lattice component, such as water or solvent of crystallizations are present, these follow the name and preceded by the number of these groups. Now, you can see in this, what does that mean? Lattice components such as water. Water of hydration, it's called as water of hydration. Now, you can see it's a this is the complex. It contains water outside the complex. Since this is also called as molecules of solvents of crystallization aerobic numericals. So now we have only one water molecule. We write as one water. Now here in this complex, two water molecules are outside. Therefore, we write it as two water molecules. So water of hydration, if it is present, we have to name the water outside the complex. This is the complex. This is the name of the complex. And one water molecule, so we write as one water molecule. If you have two water molecules, write it as two water molecules. Two water molecules. Did you understand? We'll learn this example. See, it's not written as one water. It is written as, in modern days, it is written as monohydrate. Mono stands for one. Here we have two water molecules, therefore it's called as dihydrate. So one water, two water is wrong. So we write it as monohydrate and what? Dihydrate. Here three water molecules, we'll write it as trihydrate, etc. It goes on like that. Followed this?
Yes, sir.
The following punctuation rules also should be followed while writing the name of the complex. The name of the complex compound should not start a capital letter. Name of the complex should not start in a complex capital letter. See here, we have four ammonia molecule, tetra, this will be small. If you write capital, it is wrong. You will lose marks easily, remember. So complex, whenever you are writing the name of the complex, it should not start with a capital letter. The full name of the complex ion should be written as one word without any gap. So there should not be any space. You can see this is one word. Here also it looks like that only, but there should not be any space. It should be written as one word. All right. The third point, there should be a gap between cation and anion. There should be a gap between what? Space between what? Cation and anion. But the cation and the anion should not have any space. The full name of non-ionic complex should be written in one word. Non-ionic complex means a complex can be neutral also. If the complex is neutral, it has to be named as one word. It has to be named as one word. Did you follow this, students?
Yes, sir.
Yeah. Now, one more part I will teach you. In the next class, we're going to learn the naming part. Now, before you start naming the molecule, you should be in a position to find the oxidation state of the central metal. How do we find the oxidation state of the central metal? As a whole, the charge on this complex is zero, neutral complex. Charge on this complex is zero. So chlorine is what charge?
-1.
Minus one.
Sir, -1.
Minus 1 into 3 is 3. Ammonia is what ligand? Neutral ligand. 0. Cobalt, we don't know oxidation number. I take it as X. So X will be equal to +3. So oxidation state of cobalt is what? +3. Now, similarly, if I take like this, Ag, NH3 twice, and Cl. What's the oxidation state of silver? The charge overall is 0. Chlorine is -1. Ammonia is a neutral ligand. 0 into 2 is 0. And silver, we take it as X.
+1.
X will be equal to +1. If you take this FeCO 5 times, as a whole, the complex has charge 0. Carbon monoxide is a neutral ligand. So 0 into 5 is 0. And iron is what? X. So what will be the X? X will be equal to 0. So this is metal atom. Here, metal is an atomic state. Metal is in what state? Atomic state. In these cases, metal are in what state? Ionic state. Did you follow this? Students, did you follow?
Yes, sir.
Likewise, you should know how to find the oxidation state. See, oxidation state of the metal. Now just we'll take this example. One example I'm going to teach and we'll stop. K3Fe, C2O4 and 3. All right, what's the charge on iron here? As a whole, the charge is 0. What is C2O4? C2O4 is oxalato. Oxalato is what dentate ligand? Oxalato is what dentate ligand? It's a bidentate ligand.
It's a bidentate,
Negatively charged bidentate ligand.
Yes, sir.
So it's -2 into 3. -2 into 3 is how much? -6. Iron, we don't know. We take it as X. Potassium is +1. +1 into 3 is 3. So X will be equal to +3. So you should be in a position to identify the type of ligands. If you identify the type of ligands, then you can be in a position to calculate the oxidation number. Otherwise, you will go wrong. So kindly try to identify different types of ligands. All right. Now, why I'm scrolling down is these things also will be there in this video. You can try to find out the oxidation states of the central metal in all these. We will learn the naming of these complexes, or if you know naming of the complexes, try naming. Otherwise, we will continue this with the next class. Thank you. Ma'am?
Thank you, sir.
Yes, ma'am. Thank you, everybody.